In this video, you will learn about exponents. Now, exponents is a quicker way to write certain forms of multiplication. So for example, here we have 5 2's being multiplied together. As we learned in a previous lesson, the numbers being multiplied together are called factors. So the 2's would be called factors. Now, instead of writing this as 5 2's like you see here, we can write this quicker by using exponents. So the 2 is the number we are multiplying together. So we can write this with a 2 here at the bottom, and then we're multiplying it together 5 times. Right, there's 5 2's. So I put a 5 up here, a little smaller, above the 2, and that is called the exponent. So 2 is called the base. Base means like the bottom, and then 5 is your exponent. So it's simply a quicker way of writing multiplication when you're multiplying the same number over and over and over again. Now in English, we would say this expression as 2 to the 5th power. If it was 4 2's, it'd be 2 to the 4th power. 3 2's, 2 to the 3rd power, etc. Now with exponents, there are 2 special names to be aware of. So the first one is when we have just 2 numbers multiplied together. So for example, if we had 4 times 4, we can write that as 4 to the 2nd power. The 4 is the base. We have 2 4's, so we put a 2 up here as your exponent. Now the special name for this one, when you have 2 of something, is we can say something squared. So this would be stated as 4 squared. And that's the same thing as saying 4 to the 2nd power. Now where does that term come from? Well, the term comes from geometry. If you had a square, so like this for example, and you had to find the area of this square, we would have the base times height, so 4 times 4, which would be 4 to the 2nd power. So because this is a square, okay, that's where the squared comes from. Because a square, you multiply 2 numbers together, the 4 and the 4. That's why anything multiplied twice, you can say that number is being squared. The other one is if you have 3 numbers multiplied together. So for example, 4 times 4 times 4. So that would be a 4 as your base. There's 3 4's, so 3 is your exponent. So we could state this as 4 to the 3rd power. The other special name we have for this is called cubed. So 4 cubed would be another way we can express this statement. Now where does this one come from? Now just like the square came from a square, the word cubed comes from a cube. Because if we had to find the volume of this cube, we find the area of the base, so area of the square, 4 times 4, times this height, which is another 4. So that would give us 4 to the 3rd power, which is what we have over here. So the cubed comes from the fact that to find the volume, we would multiply a number 3 times together. Alright, so now let's work with solving some expressions. Here we have 2 to the 5th power. What that means is that we have 2 multiplied together 5 times. So 2 times 2 times 2 times 2 times 2. So that would give me 4, 8, 16, 32 as my answer. Now what about 2 to the 4th power? Well, 2 to the 4th power is 4 2's multiplied together. So 2 times 2 times 2 times 2, that would give me 16. 2 to the 3rd power, or 2 cubed, would be 2 times 2 times 2, which is 8. 2 squared, or 2 to the 2nd power, means we have 2 2's, which would be 4. 2 to the 1st power means we have just 1 2 multiplied together, which would be 2. So notice the pattern. Okay, the exponent is decreasing by 1 every time. So we have 5, 4, 3, 2, 1. So to keep that pattern going, the next exponent would be 0. So 2 to the 0 power. Now look at the right side. We have 32, and then 16, and then 8, then 4, then 2. What is the pattern on this right side? Well, notice each number is 1/2 of the one before it. 16 is half of 32, 8 is half of 16, and etc. So to keep this pattern going, I need to find half of 2, which would be 1. So notice 2 to the 0 power is 1. And in fact, anything to the 0 power is 1. We can have 3,267 to the 0 power. That would still equal 1. We can have this really complicated expression right here, raised to the 0 power. That would still equal 1. So anything to the 0 power will always equal 1. Now let's continue this pattern even further. On the left side, we had 5, 4, 3, 2, 1, 0. So to keep the pattern going, the next number would be -1. So we have 2 to the -1st power. So on the right side, keep the pattern going. So each time we're multiplying by 1/2. So 1/2 of 1 would simply be 1/2. Or I can think of this as 1 over 2 to the 1st power. That is the same thing, because 2 to the 1st power is just 2. All right, keep the pattern going again. On the left side, the next exponent would be a -2, so 2 to the -2nd power. On the right side, keep the pattern going. 1/2 of 1/2 would be 1/4. And 4, we can think of that as 2 squared, 2 times 2, or 2 to the 2nd power. So notice the negative exponent simply means we have a fraction. So the negative exponent makes this into a fraction where we have 1 over, and then in this case is 2, and then the exponent becomes positive, so 2 to the 1st power. 2 to the -2nd power is 1 over 2 to the +2nd power. So make sure you know how to represent negative exponents as fractions, and then fractions with negative exponents. And we'll get some examples here in the next few slides. Okay, here are some examples. We have 6 4s being multiplied together, and you are told to write this with exponents. So because we have 6 4s being multiplied together, this would be 4 and then raised to the 6th power. So this would be a 6, not a 5. So 4 to the 6th power. So the base is 4, and your exponent would be 6. Here we have 1, 2, 3, 4, 5, 6, 7, 8 7s being multiplied together. So the base would be 7, and the exponent would be 8. So this would be written as 7 to the 8th power. Here we have 4 8s multiplied together. So the base is 8, the exponent is 4, so I write this as 8 to the 4th power. Next we have 1 over 3 times 3 times 3 times 3. So the denominator, or the bottom of the fraction, we have 4 3s. So the base is 3, and the exponent would be 4. So I can write this as 1 over 3 to the 4th power. Now remember that we can also write this with a negative exponent. So the instructions state to write this with no fractions. So we must get rid of the fraction by making this into a negative exponent. So to get rid of the fraction, what I'm doing is I write this as 3 to the -4th power. That is the same thing as 1 over 3 to the positive 4th power. Here's another example. 1 over 2 times 2 times 2. In the bottom, we have 3 2's multiplied together, so I can write this as 2 to the 3rd power. So 1 over 2 to the 3rd power. And then writing this again with no fractions, I need to get rid of the fraction by making this into a negative exponent. So instead of 1 over 2 to the positive 3rd power, I can write this as 2 to the negative 3rd power. Next we have 1 over, and that's 6 5s. So I can write this as 1 over 5 to the 6th power. And again, we want to get rid of the fractions by writing this with a negative exponent. So I can write this as 5 to the negative 6th power. Next we have negative 2 times negative 2 times negative 2 times negative 2. So we have 4 negative 2's multiplied together. So negative 2 is my base, and then 4 is my exponent. So I can write this as negative 2 to the 4th power. Okay, there's a term we have that's called a variable. A variable is simply a letter to represent some unknown number. So for example, we have x times x times x times x. What that means is we have 4 numbers, or I guess one number multiplied together 4 times. So it could be any number, it could be 1, it could be 2, whatever. But the rules are the same with variables as they are with actual numbers, because a variable is representing a number. So to write this with exponents, we have 4 x's. So x is your base, and then 4 would be your exponent. So this would be written as x to the 4th power. If you are told to write an expanded form means you simply write the problem out. So instead of 5 squared, we would have 5 times 5. Instead of b to the 6th power, we have 6 b's multiplied together. Negative 2 to the 3rd power would be 3 negative 2's multiplied together. Here we have negative 2 to the 3rd. Notice the exponent is just with the 2. It's different than the question up here. So we simply raise 2 to the 3rd power. So we have 3 2's, and then the negative is out in front after the fact. Okay, next we need to work with exponents to simplify in particular cases. Here we see 2 to the 4th power plus negative 3 cubed. So we take care of the exponents. 2 to the 4th power means 2 times 2 times 2 times 2, which would be 16. Negative 3 cubed would be negative 3 times negative 3, which would be a positive 9, and then times another negative 3, which would now be a negative 27. So what I have is 16 plus a negative 27. So when I add and the signs are different, I need to subtract the bigger by the smaller, so 27 minus 16. And then I keep the sign of the bigger. So 27 is bigger and it's negative, so this solution would be a negative 11. Here we see 4 squared times 2 cubed minus 3 squared. So I need to begin within the parentheses first. So I do this first. 2 cubed would be 2 times 2 times 2, which is 8. 3 squared is 3 times 3, which is 9. So we have 4 squared times 8 minus 9. Okay, well 8 minus 9 would be negative 1. So 4 squared is 4 times 4, that's 16. So I have 16 times a negative 1, which would be a negative 16. So my solution is negative 16. I'm going to walk you through a couple more examples here. Next example, we have 5 squared times 2 squared divided by 10. So 5 squared is 5 times 5, which is 25. 2 squared is 2 times 2, which is 4. So we have 25 times 4 divided by 10. 25 times 4 is 100. 100 divided by 10 would be 10. Next we have 15 to the first power times 22 to the 0 power. So 15 to the first power means we have just one 15, which is 15. And then anything to the 0 power will always equal 1. So we have 15 times 1. Well, 15 times 1 is just going to be 15. Now with exponents, there are different properties that we have. There are 3 properties we will discuss. First, we have the multiplication property. And that says that if we have 2 or more values multiplied together and the base is the same, I will add the exponents. So for example, here we have x squared times x to the 4th power. X squared means we have 2 x's. X to the 4th power means we have 4 x's. So the x times x, here we have 2 factors, or 2 numbers multiplied together. X to the 4th power, we have 4 factors, or 4 numbers multiplied together. So altogether, we have 2 plus 4, or 6 factors being multiplied together. So I can write this as x to the 6th power. So notice we simply added the 2 plus 4 to get 6. So in general, if we had anything to the m power times anything to the n power, there's m a's here. So this is kind of confusing without the numbers anymore. But here there are m a's. That's the number of factors, m factors. Times, here we have n factors of a. And together we have m plus n factors of a. So all I do is I keep the base. So the a is my base. And my exponent would be simply m plus n. So the rule is you add the exponents. Okay? So let's look at some examples where we can use this. Here we have 3 squared times 3 to the 3rd power. If you go through the long way, you would see that there are 2 3's times 3 3's, which would now give me 5 3's. So my solution, my simplified form, would be 3 to the 5th power. So we simply take the 2 plus the 3 to get 5. Alright, so we have the same thing again for some reason, so ignore that. Next example, we have x squared times x to the 6th power. So instead of going through all of this where we write out 2 x's and then 6 x's, we can just skip to the shortcut, to the rule, which says we can add the exponents. So we can add the 2 and the 6 to get 8 as my exponent. So my solution would be x to the 8th power. If we had b to the 5th power times b squared, we're multiplying, so we add the exponents. 5 plus 2 to get 7. So this can be written as b to the 7th power. Now what if you combine numbers with variables? Well, we just simply multiply the numbers together. So the 3 times 4 would give me 12. And then look at the m's. M cubed times m to the 4th power. You're multiplying, the bases are the same, they're both m, so I can add the exponents. So this would be m to the 7th power. So my final solution would be 12 times m to the 7th power. Now what if you throw in numbers plus multiple different variables? So same idea. We look at the numbers, negative 2 times 5, and that gives me negative 10. Look at the a's. We have 3 a's times, here it's an assumed 1. We have 1a, a to the 1st power. So 3a's plus 1a gives me 4a's. So now this is a to the 4th power. And then the b's, we have 2 b's and then 3 more b's multiplied together. We add the exponents, 2 plus 3 to get 5. So we have b to the 5th power. So my solution is negative 10 times a to the 4th power times b to the 5th power. So now with division, division is similar, where instead of adding the exponents for multiplication, instead we're going to subtract the exponents for division. So the rule is written right here, which is kind of maybe confusing to understand without the numbers. So let's look at some examples. Here we have 2 to the 5th power divided by 2 to the 3rd power. Well, 2 to the 5th means we have 5 2's. 2 to the 3rd means we have 3 2's. So I could use, the fraction rules where I can divide out the common factors. So like the 2 here divides with the 2 here. This 2 can divide with this 2 with this 2. So that leaves me with 2 times 2, or 2 squared, on the top. Using the property, we can simply subtract the exponents. So the 5 minus 3 would give me 2. So we have 2 to the 2nd power. Here we have 3 to the 4th power divided by 3 to the 2nd power. I'm dividing, so I can think of this as a fraction if I wanted. So we have 4 3's divided by 2 3's. So yes, things would cancel. The 3's here and the 3's here would cancel, leaving me with 3 times 3, or 3 squared, on the top. But I don't want to have to write it out every time, so I could just do the division property, subtract the exponents 4 minus 2 to get 2 as my exponent. Either way, I get 3 to the 2nd power, or 3 squared, as my solution. Okay, here we're combining division and multiplication. We have y to the 8th power divided by y cubed times y to the 4th power. So looking at the denominator, y to the 3rd power times y to the 4th power, we add the exponents when we're multiplying. So 3 plus 4 gives me 7. So I now have y to the 8th power divided by y to the 7th power. Now with division, I can subtract the exponents. 8 minus 7 would give me 1. So my answer is y to the 1st power, which is the same thing as saying y. Next we have 5 to the 4th power divided by 5 to the 4th power. So here, different ways you can think of this. If we just simply subtract the exponents, the 4 minus 4 would give me 0. So we would have 5 to the 0 power. We know anything to the 0 power will always equal 1. That's one way to think of it. Another way is we're dividing the two of the same numbers together. Anytime we divide the same number, we're going to get 1. So whether it be 4 divided by 4, or 3 divided by 3, or in this case 5 to the 4th divided by 5 to the 4th, it will always equal 1. Or if we wanted to write this out as 4 5's and then divided by 4 5's, once again we could also divide these out, and if we follow the division rules, we would get those to cancel. So we have 1 times 1 times 1 times 1 over 1 times 1 times 1 times 1, which would still equal 1. So bottom line, our answer will equal 1. Lastly, we have what's called the power property. And that is if we have a power to a power, or two different exponents in the same expression. Here we have x to the 5th power, and then that expression is raised to the 3rd power. So to illustrate the principle behind the rule, in this case we would have x to the 5th multiplied by itself 3 times. So we have x to the 5th times x to the 5th times x to the 5th. That is what this 3 here means. We have 3x to the 5th. So with multiplication, we know that we add the exponents. So we'd add 5 plus 5 plus 5 to get x to the 15th power. So notice where the 15 came from. We took the 5 times the 3, and that would give me 15. So the rule in general, if I have anything, so a to the m power, raise that to the n power, we simply multiply the exponents. And here we see it illustrated kind of complicated in a complicated way without numbers or anything. But if we have here a to the m to the n power, we would multiply a to the m over and over again n number of times. So we have multiply n times together. So I would add all the m's together because I'm multiplying. When I add them together, I get m plus m plus m, and I keep going. And if I keep going, I'm going n for n terms, so we have m times n as the exponent. That's very complicated to understand if you don't quite comprehend. It's not a huge deal as long as you know how to use the property. The property, bottom line, if you have a power to a power, you multiply the exponents. Okay, let's look at a couple quick examples. Here we have 4 to the 6th power, raise that to the 5th power. You have a power to a power, you multiply 6 times 5, and that gives me 4 to the 30th power. Here we have 3 to the 5th power times 3 squared. Be careful, we don't have a power to a power. What we have is multiplication. So here we add the exponents, 5 plus 2, to get 7. So we have 3 to the 7th power. Here we have a combination of multiplication as well as the power rule. So here we have a power to a power. X to the 3rd power, raise that to the 2nd power. Power to a power, we multiply, so 3 times 2 is 6. So we have x to the 5th power times x to the 6th power. And now with multiplication, we add the exponents, 5 plus 6, to get 11. So my solution is x to the 11th power. Next we have y to the 3rd power times y to the 5th power. All of that is raised to the 6th power. So within the parentheses, we have to multiply. So y to the 3rd times y to the 5th. So when you multiply, you add the exponents. So we have 3 plus 5 gives me 8. So we have y to the 8th power, raise that to the 6th power. Power to a power, we multiply the exponents. So 8 times 6 gives me y to the 48th power. Next we have 5 squared times 5 to the 4th times 5 to the 8th power. This is all multiplication, so I simply add the exponents. 2 plus 4 plus 8 would give me 14. So my solution is 5 to the 14th power. And that concludes our lesson for today.